So, continuing with our discussion on software-defined networking, one thing that we mentioned before we left off is that there are a lot of different examples of alternative APIs. So that's the thing that basically um, there's really no standardization on today. So we're going to talk about some of these in some level of detail throughout this lecture. So one thing to keep in mind is that some of the APIs that are actually used previously had a different function, a different usage than how they're currently being used to support software-defined networking. So in addition to what we talked about previously with the OpenFlow, there are additional APIs such as XMPP that's used by Juniper Networks and 1PK that's used by Cisco. And there's others besides those. We're also going to see is that, like I said, a lot of these can sometimes be adaptations that have previously different functions. Same thing with northbound APIs. A lot of different ones here. We're going to focus on Alto, which was originally used for peer-to-peer networks. Then we have different type of overlays. We have mentioned the VXLAN for virtual LAN overlays, and there's other overlays, including layer 2 and layer 3 VPN, and Trill, and Lisp, etc. There's network configuration APIs such as NetConf, and there's different controllers such as PCE and Forces, and we're going to take a look at both of those. So let's take a look first of all at XMPP. And basically, originally what XMPP was originally used for, believe it or not, it was not designed for SDN. In fact, it precedes SDN. And it was originally designed for Skype, basically as a message and presence protocol. So it's basically used to send messages. And presence protocol basically means it's a way of letting you know that a certain user is available. So you go on Skype and you know for the people in your group who's online. And that's kind of what XMPP does. XMP is extensible, so we can add fields. It uses XML. And basically XMPP works very similar to Simple Mail Transport Protocol, except that it's used for near real-time communication, such as chat, like a chat type of communication. So it responds, quickly and basically near real time. So each client has an ID, and this particular one is an ID of a person's mobile phone. So basically, the ID is basically tied to a particular device. You have clients set up a connection with the server. So you have an XMPP client and server. Once the client is online, it automatically sets up a connection with the server. So like I said, there's two capabilities. One is two protocols, two parts of the protocol, I should say. One is presence. So the server maintains a contact address and may let other contacts know that a particular client is now online, so they get some sort of status update. So if you have a closed group, you can basically know what members of your closed group is currently online. And then it is also there's also a messaging part of the protocol. So when the client sends a chat message to another client, it is forwarded to these other clients. And so unlike mail, the messages are pushed in real time as opposed to being pulled like you do with a SMTP POP email. So basically the messages get pushed to the recipient rather than the recipient trying to get the message from some source. So the question is, how does this get used in a software-defined network? Well, first a little bit of background. So XMPP basically is the IETF standardization of the Jabber protocol. So Jabber protocol was a very successful chat protocol that basically the IETF took and made it into a standard. So there's an RFC 6121 that defines XMPP using TCP connections. However, HTTP is often used as a transport these days, so you can navigate through firewalls. This way I don't have to worry about blocked ports. So all messages in XML are encoded, and XML is usually not efficient for binary file transfers because you have to convert everything to ASCII. So basically people generally don't use it for binary file transfers. And one of the nice things about XMPP is that so if you want to do binary transfers, you usually have an out-of-bound binary channel that's used in conjunction with XMPP. The nice thing about XMPP is there are a number of open source implementations available. That's why you find XMPP used in most instant messaging programs such as Google Talk, Skype, the messaging part of Facebook, as well as the chat capability in many games. So lately XMPP has found a new use in software-defined networking to basically be used for basically data management or network management. So it's a way that network devices can send information to each other. So basically it kind of replaces the old command line interface, and so now network devices have XMPP clients that respond to XMPP messages that contain command line interface management requests. And this allows you to manage your network using any other XMPP client. You could even use your smartphone. So this gives you a lot of flexibility in the network, and you don't have to worry about doing a remote, having some sort of remote telnet session to bring up the command line. It gives you another option for communication. And this is currently used by switches such as Arista. Arista switches can be managed by XMPP, and Juniper routers use XMPP as a southbound protocol for SDN. So the way XMPP works in a data center is that everybody is an XMPP client, and they can all communicate to an XMPP server. The nice thing about XMPP, since it's used for chat, and in chat you basically can set up contact lists, so you have some sort of privacy. It has built-in authorization. So some of the security is built right in. So this basically provides a lot of the capabilities that you would want to do remote management without having to design a new protocol. Basically just took an existing protocol and basically used it for a function other than what it was originally intended. The next thing we want to talk about is Path Computation Element, or PCE. So if we go back, we can see that PCE is a controller API. So when you're doing MPLS or GMPLS, you have to have an originating router to find the path that will satisfy multiple constraints that have been set up for that path, including not using any backup routers and having to use a given bandwidth. So to set up this information, set up this path information, that requires a lot of computer power, and it basically can be more than more computer power and more end-to-end knowledge, network knowledge of the path than a router is able to support. So the IETF PCE working group developed a set of protocols that allow a path computation client, in other words a router, to get a path from a path computation element. And just so you don't get confused, a path computation element is really a path computation server. So this protocol, believe it or not, basically predates OpenFlow. So OpenFlow kind of took some of this and basically added to it. So the idea is that let's say there's a client that wants to send a path, and the path has some constraints, and the constraints are: I need to set up a 1 gigabit per second route. I need to go to New York, but my constraint is I don't want to go through Boston. So what happens is it talks to the server, the path computation element, and basically the server gathers data in a traffic engineering database and is able to provide that information back to the client. So the PCE, way it works, it separates the route computation function from the forwarding function. So you're seeing this very first step in separating control from forwarding. But this PCE server doesn't matter where it's resident. Both functions can be resident in the same box or different boxes. Now we tend to think of clients and servers as two different machines, but client and server are basically just two different functions, and these functions can reside everywhere, anywhere. So there's a lot, if you want to dig into it, there's a lot of documentations of 25 RFCs that document the protocols for PCE to PCC communication between client and server. If you have multiple servers in a network, you have to have PCE to PCE communication so that they are able to share data with each other. And then the client has to discover the PCE, so there's also protocols for PCE discovery. Another controller that's available that was started in 2001 is the Forwarding and Control Element Separation Protocol, or FORCES. So back in 2001, the IETF basically got the idea that we should separate the control and the forwarding planes. So basically they came up with what was called FORCES, for Forwarding and Control Element Separation, or FORCES. Basically, FORCES is made of control elements that prepare routing tables for use by forwarding elements. And each control element may interact with one or more forwarding element. And the control elements and forwarding elements are basically managed by the controlling element manager, and the forwarding elements by the forwarding element manager. So you kind of have a tree structure, or at the top of the tree, you have your control element manager controlling control elements. Each one of them can be connected to one or more forwarding elements, and then you have a forwarding manager that coordinates between the forwarding elements. So this, of course, begs the question of what is passed between them. From a historical point of view, the idea of control and data plane separation was first used in BSD 4.4 routing sockets in the early 1990s. This allowed routing tables to be controlled by a simple command line or by a route daemon. So below we have the different type of exchanges that the Forces protocol can support. So it can support the exchange of information such as port type, link speed, and IP address between the control and forwarding elements. It can set up IPv4 or IPv6 unicast or multicast forwarding. It can be used to set up quality of service parameters, including metering, policing, shaping, and queuing. It can support packet classification, and it can even support high-touch functions, basically functions that actually change information in the packets, such as network address translation and application level gateways. It can also encrypt packets, and it can provide management information. Basically, it can provide the measurement and reporting of per flow traffic information. So in order for all this to work, we start off with the forwarding element manager and the control element manager communicating with each other. This starts off first with a security exchange. So they're authenticated, and once that occurs, the controlling element manager sends its list of controlling elements and their attributes to the forwarding element manager, and likewise the forwarding element manager sends a list of forwarding elements and their attributes. From this point, the forwarding element manager basically connects to the forwarding elements under its control versus a security exchange. Then the forwarding element responds with their forwarding element IDs and attributes, and now the forwarding elements receive the control element ID that forwarding element is going to be communicating with. Likewise, the controller element manager will basically have a security exchange with its controller element, basically authenticating. That control element sends its ID and attributes, and based on that, the controlling element manager tells it which forwarding element ID it's going to be communicating with. Then once that process is complete, the forwarding element and controller element can communicate with each other, starting off by a security exchange to authenticate, then the forwarding element ID and attribute, and then the initial configuration for the foreign element, and then it can make changes going forward. It can add routes. It can ask for statistics. It can, for the foreign element, can provide status such as a port is down, and the controlling element can send data to the foreign element such as a new forwarding table to use. Another type of API that is used is the application layer traffic optimization. As we mentioned way back here, this is basically a northbound API. So basically, just like XMPP, Alto had a different original use. The original use for Alto was basically developed by IETF, the IETF working group, to optimize peer-to-peer traffic. So the idea is, as we've spoken previously, peers communicate in kind of a random fashion. So it's very possible for the next peer that you're using, if you could be in the United States, to be, communicating with a peer from Germany, basically wasting network resources. So Alto was actually originally set up to provide better guidance in peer selection, with the whole idea of to find give some criteria and help peers make better choices of what peers they communicate with. So based on that, Alto basically has a client-server paradigm where the Alto server has knowledge of all the distributed resources in a peer-to-peer network. And basically, the clients basically go to the Alto server to request information about the appropriate peers that it should be joining with. And basically this is determined based on different types of criteria, such as physical distance and maybe the traffic charges for a particular connection, etc. The Alto server also gets information from providers and from nodes about their characteristics. So, for example, it might get information about the different charging rates used by a particular provider. Likewise, the client can actually send information back get information from peers that it's aware of and send it back to the server, and then based on the criteria, the server can come back with an ordered list, prioritized list, basically saying which is the best peer to connect to. And also included, there's also a server discovery protocol that's part of Alto, so that the client can discover what server to use. So Alto basically has been basically extended, and basically its new role in a data center is, instead of locating peers, it's basically used to locate resources within different data centers. So now this course works very well in a dynamic environment where you have different data centers that you may have to work with, and you need to check on things. So you need to know what resources are available. So basically, you may have the need for so much memory or storage or CPU or networking bandwidth. So Alto can be used to find out that information. It can also find out the cost of resources, just like it could find out the cost of a provider. It can provide information on constraints on resources. Maybe you have only so much bandwidth available at a particular data center, and as well as constraints on structure such as power consumption. So now Alto is now used to provide, basically it's a management tool and a configuration tool to basically help you configure your connections and choose the right data center, which is very important in a dynamic configuration such as in a cloud computer environment. Likewise, the Alto client can get information from various providers as well and pass that on to the server, just like it could get information from various peers in a peer-to-peer network. Unfortunately, one of the issues is that Alto is not set up to support resource privacy, and it also has the issue where it also has the issue with not getting all the cost information from a provider that it could that we would want it to get. So those are basically some areas of improvement that need to occur in using Alto. Next, we're going to talk a little bit things on a little bit more from a philosophical point of view. So basically, as you can see, if you go through and do any type of searches on SDN, you're going to see that a lot of things are not very clear. And so there are things that are still in flux with SDN. So it's not really as cut and dry, and it's still experiencing some growing pains. There's not a lot of standardization, and you basically, it's very difficult to. There's not basically a standard way to do SDN. So this is basically still being sorted out. Some other things to talk about on that vein is SDN is easy if the control plane is centralized, but it's not necessary to have a control plane, a centralized control plane. It probably really is for our discussion as far as cloud computing, but in other applications, sometimes you can actually have a distributed or partially distributed control plane, which you may need to bring in legacy equipment or to have a fail-safe operation. You usually have to have some sort of backup with your, at least have some sort of backup with your control plane, because if you lose access to that, then you're going to bring your whole network down. And sometimes, so going with that, the complete removal of the control plane can be harmful. There might be some applications that won't work very well with separating the control plane from the data plane, and then you also have the problem with the problem with failure. Another thing that you'll find too, if you look at different SDN implementations, is there's not a very exact division of where the control plane ends and the forwarding plane begins. So that's something that's still being worked out. If you're using something like OpenFlow as your standard southbound protocol, it makes it easy to set up, but there are some limitations in communicating with other networks, maybe even limitations in possible networking products. So what you're going to find is that there's no one protocol that's going to totally work for everything. It's kind of like there's no standard operating system. You don't have everybody that just uses Windows. There's no standard processor type, and there's no standard type of router or Ethernet switch. The same thing is going to be true, at least for a while, with the different APIs and protocols that are used by SDN. And the fear and the concern is there's a possibility that, as companies invest in SDN, and the concern is that something less complicated might come along and replace it. This is very similar to the back about 10 years ago when ATM was seen to be a potential and very promising network technology because it had quality of service and its virtual circuit capability. But of course it was very expensive, and it meant changing out your whole network infrastructure. And then MPLS came along and had a lot of those same capabilities for not for a lot less work. So the concern is this might happen with SDN as well. So let's take a look at what a SDN controller function might look like.